For SP-19, the group wanted to ask themselves the question, what kind of language do we wanted to make? And by elaborating on that, we were able to ask what each of us liked for particular languages and what each of us disliked about particular languages. And each member was to come up with like a bulleted list of stuff that explained these details. And after moments of discussion, we decided to settle on the idea of implementing type conditions as a feature to our language. And with these type conditions, there are going to be extra restrictions that will be applied to specific types. And for instance, if we're essentially trying to iterate through an array, we want to make sure that the current index value that has been passed in is a non-negative number and it's within the length of the array, so that we don't run into any out of bounds issues that could have otherwise occurred. And with these type conditions, we can impose them on specific variables, and this will be referred to as type narrowing. And for instance, the type narrowing would just essentially quote unquote narrow the type of the variable if it's considered for that condition. So as a quick example, without trying to go into too much details, I have defined here a print position method. And with this print position method, one of its parameters will be taking in a variable of type int. And this will only occur if the variable of type int is number greater than 0, which means it has to be a positive number. Now, when this method has been called successfully, it will invoke upon one of our custom methods that will just print output to the console the number that it happened. Okay. The next thing we wanted to figure out about type conditions was to work on the grammar of the language. We thought about how functionality of the grammar could be applicable and how specific it was. And this would essentially apply to any basic constructs that the language would apply, be any conditional statements, any expressions, and along with the grammar, we decided to write down the detailed semantics of each of these rules and try to cover all the potential edge cases so that this implementation would have been simple as possible. Now, in our efforts to implement most of these rules, we unfortunately ran into some issues, which did not pose any significant setbacks, but made things more difficult or more time-consuming as the process continued. In our efforts to try to implement certain things for our language, there is one major design flaw that we had to essentially deal with / fix. Our original design was for arrays to be mutable, meaning that each individual element of them could be changed without creating entirely new arrays. However, this allowed any specific users to change the properties of the arrays that might be restricted by type conditions, such as these type conditions will become false without the compiler knowing about it. And our solution was to just make arrays mutable, meaning that they cannot be changed without making new arrays. And to offset this heavy restriction, we essentially borrowed specific array manipulation features called slicing and spreading from other languages, which allows the array to be used in expressive ways without this whole mutability issue. Spreading of slicing will essentially be more applicable or more explainable if you were to do some research on this, but in terms of this video demo, I'm going to ignore that for now. So, as you can see, for example, here, this particular condition here and this particular condition here. This slide starts off by creating an array of ints, hard-coded with the values 1, 2, and 3. Now, this line below will essentially try to make a copy of array 1 into array 2. However, this particular example especially will show off something called aliasing, where two objects refer to the same thing. Now, at this point here, this immutability issue might be terrible here, because if we're checking for the array 1, where this index is a number greater than 1 or greater than 0, we're going to manipulate the other array and just set this equal here. And now if we were to call this print position method, which has been defined here, this would cause an issue. And it's because that whatever happens to array 2, mutability wise, happens to array 1, since these things are going to exhibit aliasing. And this is one of the reasons why we wanted to make arrays mutable as well as strings. But this is more applicable to arrays since they're more hard to deal with. From previous research into the subject, I had mentioned something about using Antler. Antler is a tool that specifies a format for language grammars, and if we given a file of grammar in that format, it will be able to generate its own lexer, parser, and a concrete syntax tree based on this grammar. Knowing this, our first step towards the implementation was to translate this grammar that we had constructed beforehand to the format specified by Antler, and in doing so, we got the first half of the code for free. Antler has been more than adequate enough to just help us with dealing with ambiguous expressions, making sure our syntax was valid, and not making us make our own abstract syntax tree, which would have taken too long. The one consideration we did have to give was learning how Antler resolves grammatical ambiguity, and literally from top to bottom in the grammar file. As we learned this, as we had essentially dealt with this issue or prevented from occurring, the lexer and parser never posed any particular problems for us. Now, in terms of what the grammar looks like, the grammar will consist of terminal symbols and non-terminal symbols, where each non-terminal symbol will essentially have to be further defined into what their necessary abstractions are. I have this file abstraction, which can be defined as multiple abstractions definition, followed by end of file. Now, all programs will essentially have to begin from here. And this multiple abstractions of definition could be split off into their own function definitions or variable definitions. And these things would essentially derive into more abstractions, where function definitions could define methods for our program. Or variable definitions define how we make a variable a particular data type, what do we assign it, and how we can essentially express it as well. And without going into too much details, some of these will essentially be repeating, but that's more about how coding or making language is essentially going to work out. Or what they further break down into. This was mentioned beforehand, but in terms of looking at a syntax tree, if we were to go to a preview, for example, we're going to create an expression called let x int colon equals 5 and a semicolon. Now, if we were to let this particular expression run, just as a quick hand notice, Antler is able to create a quick syntax tree for that just particular syntax here. And the parse tree, we start with a file, the definition, a variable definition, and each variable definition will be consistent with whatever is from here. Where this let keyword here, ID will just be whatever x is. Type, which is going to be a simple type, which breaks down to be the integer or an int. And we have this colon expression, colon equals syntax, just to make it more clear what our intent is. Or more clear for people to not confuse it with other operators that do different things. And this value of 5 here will just be an expression, which breaks down further into a literal factor, then a literal, and then an integer literal. Now, in terms of trying to make sure this thing runs properly through our grammar file, it will work as intended. Okay. Just to show that some of the syntax of the language worked properly, I have made myself a main.pint file, and in this main.pint file, I just have some example syntax I'm likely going to show off. Right here, I have defined a function called main, and this function's return type is unit, meaning that it should not return anything. Now inside this main function, the first thing to occur would just be print out hello world to the console screen. And this println is going to be like a standard library function, helps us output stuff to console. Now the next set of code or lines of code will be useful just to create variables of type int and assigning values to them. And we're essentially going to be using these when we get to that point. Now the first part here will just be this if statement. This if statement, when it calls upon the print position method, show off the output of this, and it'll exemplify type narrowing. The type narrowing condition has been specified here, so that this function will have to work, assuming this if statement gets hit. So if var I is greater than 0, then call print position on it. And we had to essentially include this as a little expression just to be consistent somewhere, just to show off this type narrowing. Now, below that, we're going to have a set of if statements here. Now, the set of if statements will be useful to show that if one condition expression could be synonymous with another condition expression. So, if result is greater than x, then go down here. And if x is less than result, then print iln summation of result. Now, since this condition here and this condition here are both true, it satisfies whatever we wanted to specifically do. And if we go to where the summation method is defined, it's going to be similar. It's going to be a recursive method that takes a value from 1 to n and just gives the total sum of all of those things. Now, below that, there's a couple examples of creating arrays. Now, this statement here will create an array of integers called AR01 and assign it to values of 1, 2, and 3. Now, below that, we have this thing here. And this thing here will essentially be used as aliasing for array 1. And any changes to array 1 will be visible within array 2. And any changes to array 2 will be visible to array 1. Now, this if statement here will have to check if the first index is a positive number. And if so, just set it to equal -1. Now, since if we were to make arrays mutable, this would have caused a problem here, because this doesn't introduce any sort of type narrowing. This wouldn't introduce any sort of type narrowing because array 2 has been changed, but not the first one. And this is because that arrays were going to originally be mutable, and displayed this concept of aliasing. Now, instead of that, we made them immutable and used specific methods instead, such as array slicing and spreading, which will essentially be useful for getting the subarray or try to change an array index without making them mutable at all. And, as an example, if we were to let this code run, I'm going to ignore these two warnings. My thing is fine. Now, before this occurs, it would have to validate if there's any specific type errors. If no type errors were occurred, then we'll execute whatever each of these statements will want to do. So the first statement would just be to output this to the console. The second outputted statement would be from this method here, because we're showing off type narrowing at this point. And the third condition would just be from this here. Since we're calling summation on this particular variable here, we're essentially getting an integer number back and then output it to the console.
To elaborate on how Pint actually functions, after we receive a concrete syntax tree from Antler, we perform two phases. The first is the type checker, and the second is the interpreter. Now, because it's a little simpler, I'll explain the interpreter first. The interpreter is the part that actually runs the code. It was originally intended to be only for the prototype, but unfortunately we didn't have time to change it for the final product, so it's still there, basically. So how does it work? Well, okay, first let me make this code a little simpler. The interpreter operates by performing a recursive descent on the concrete syntax tree, which is very similar to a post-order traversal. Basically, so the first couple nodes, the file, the definitions, are done a little differently, but the main body of code, the function bodies, operate in the manner I'm about to describe. Basically, the idea is that we will go down to the lowest nodes, establish a value for them. So, for instance, where's a good place here? We'll first establish the value of the 5, and then we'll go back up. So this has value 5, that is value 5, that all have value 5 because they're most of these are essentially implementation details. And then the next node is a multiplication sign, so that doesn't have a value per se, but we'll use it in a bit. And then we'll go all the way down to the 2 right here and establish its value as, well, a 2, and then go back up the tree up to this multiplication node. Now that we have all the children, we can actually establish a value, 5 times 2, 10, and that is now the value of the whole multiplication node. And like I said, that's basically how the majority of the interpreter functions. Where this differs slightly from the post-order traversal is that some nodes may not get visited at all, or may get visited multiple times. For instance, in this if statement, which is right here, then first we'll evaluate the condition, which is right here. We'll get a value for that, and only if it's true, which in this case it is, will we visit the body. Whereas in a normal post order, you would definitely visit every node, or traverse every node, I suppose I should say. Whereas in this, like I said, if the condition is false, you simply will not visit that. Or similarly, if we had a while loop, like so, then we can visit the body node multiple times, depending on, again, how many times the condition is true, which, again, in a post order, you traverse each node exactly once. And the other thing that's similar, the only other difference, I suppose, is that function nodes, despite the fact that they're just a name, there's nothing, they have no children to visit, function call nodes, I suppose. Logically, the bodies of that function become the children of that node. So it'll actually visit the bodies, or the body function, or the body nodes of that function in place of where the function is evaluated. Yeah, so that's basically how the interpreter works. The type checker, like I said, is a little more complicated. It basically checks, it checks the types, shocker, uh, to make sure that we don't do anything illegal. Like, for instance, we could say I is an int, but assign it a string, right? That is bad. That's what the type checker basically checks for. And if it finds any, then we don't run the interpreter. Now, the type checker is actually a proper post order, because we have to check the type of all the code regardless of whether or not it's actually going to get run. It differs also from the interpreter in that we don't actually evaluate any code. We just look at it and see what type it should have, right? So, for instance, a loop, we don't run it over and over again. We just figure out what type the loop should have. And a function, we don't actually go and evaluate the function. We already know what type it should have, right? So in this case, it will just go and visit each and every each and every child, and then only after it has done so, it will get a type for itself. So that's generally how the type checker works, but the reason why it's more complicated than the interpreter is because it contains type conditions. And type conditions were by far the hardest part to implement. Hard enough, in fact, that at one point we realized that our implementation had an enormous bug and we just had to redo like half of it. So in order to implement type conditions, there are two things we need. Firstly, we need type narrowing. And secondly, we need to verify that the types of things that, or the narrowed types, right? So I in here has a narrowed type. We need to verify that it actually meets this condition. So type narrowing wasn't too hard. We are already keeping track of what variables exist and what their types are, so that, for instance, we can tell that this actually is an int, right? We have to know it's an int from here in order to know it's an int, to know that we can actually call the function with it. So we basically just, every time there's an if statement or a while statement, we look at its condition and all the variables that are used in it. We narrow its type to just that whole condition, but where that variable has been replaced with it. And we apply that narrowed type, like we modify the type, the variable's type, to be that narrowed type, but only within that body where the condition actually applies. That's easy enough, and that is the only part that we didn't have to redo of type conditions at any point. The hard part is figuring out that two conditions are equal, or rather are equivalent, because one of the big things is that they don't necessarily have to be equal. In this case, they would be, but we can very trivially say, just turn that around, and now we're doing two different operations on on, well, the same operands, but in a different order, which in general is very much not the same thing. So we need to figure out how to verify that those are in fact the same condition. Now, our original approach was we would basically take what's called an abstract syntax tree, which is basically where we take the concrete syntax tree and remove all the unimportant parts. Like, for instance, if we look at this node right here, then we can see that the curly braces are actually part of the tree. We don't really care. We know there are curly braces. So the abstract syntax tree doesn't have those. But the other advantage, the more important advantage of an abstract syntax tree was that we could add type information. So the idea was that the type checker would check the types and then store that type information in the abstract syntax tree, so a later use could have that type information without checking all over again. But unfortunately, like I said, we're still on using the interpreter, which does operate on the concrete syntax tree because the type checker and interpreter were made at the same time. So we're not actually using that type information anywhere, despite what we had planned to do. The original plan was to store the abstract syntax tree and just compare those for equality. But again, that has the problem that these two conditions are very much not the same thing, just from a abstract syntax tree level. When we found out that wouldn't work, we basically made a duplicate of the abstract syntax tree, but with a couple big differences. Firstly, it doesn't support all of the nodes. For instance, loops cannot be represented in our duplicate of the abstract syntax tree, which basically means that we're banning loops from the type conditions because that's just plain old confusing, really. So we decided that's probably a good idea. But the bigger difference with the duplicate is that it has, instead of using variables or it has an idea called inputs. And basically each input in a condition represents, it could represent a variable or any other expression that might have, that might meet the condition. So for instance, we could write this, and obviously I haven't said what array is, but let's say there's an array somewhere, right? And we want to check that some particular index it meets a condition, and then call a function that requires that condition. An input could represent that expression right there. And that allows things like this. And the third and final difference between the AST, or abstract syntax tree, and this duplicate we made was that we can define a more complicated relationship such that things like these can be equivalent. So yeah, that is basically a nutshell of how the type checker works.